Hi guys, Harry here. Welcome to Scrap Science. So I'm making another heavy water video, part 5 I believe, simply because we've got a little bit of stuff to do because we're nearing the very end of the enrichment process. So we've got quite a bit of stuff to do in quite a short amount of time. Anyway, I've had this cell running down here for the last couple of weeks, just running it very slowly. That's not looking too good. There we are. I've had it running at a little bit over an amp for all that time, and so I haven't really looked in there, but what we should have left in there is a volume of around 100 milliliters of water. So we've reached the point where I think now's the time to do the last large-scale distillation. Right, because once we get down to really small volumes, it's going to be all the water droplets that are going to be left inside all of the distillation apparatus. Is going to be quite a significant loss. So I think 100 milliliters, now's the time to do it. So what I'm going to do is I'm going to stop the electrolysis. I'm going to take all the water out. I'm going to neutralize the sodium carbonate electrolyte to make some sodium sulfate, which should be a little bit easier to get all the water out of. And then we'll distill that 100 milliliters or so. The reason that we're distilling it is because once we reduce the volume by a certain amount, all of the sodium carbonate electrolyte in there will actually start crystallizing out, which has happened before, and it was a massive pain to try to fix that. So we're just going to distill it, make sure we've got pure water for the next stages of enrichment. Also, I've cleaned up the desk, so it's looking way nicer than it was before. Remember, we had all these bottles of stuff all over the back of the desk. I put them all down. The bottom, nice and neat, and all of this stuff I've just got out now. All of that stuff will be packed away at the end, and it'll look very, very nice. And there it is. I've taken out the heavy water cell. You can see that in a container that we used last time, and the rest of our concentrated heavy water surrounding it there. You can't really see on camera. Can I zoom in? Oh yeah, I can. That's where the water level is on the inside of the container, and this is the rest of it. So I've been swapping out like which set of water is on the outside of the container and which of it's on the inside, so that we evenly kind of concentrate the heavy water. And I think maybe we're not quite down to 100 milliliters yet, but we have reduced the volume quite substantially over the last couple of weeks, I think. So I've added all of our heavy water concentrate into this round bottom flask. And you can see it fills up a little bit over half of the flask, and the flask is a 250 ml flask. So we've probably got around 130 milliliters of water left at this point. What I'll do now is, did I mention that I neutralized all of the sodium carbonate with sodium bisulfate? If I didn't, then there you go, I did do that. What we're going to do now is just stick this in the heating mantle, and we'll set up a distillation for it. And I've set up a nice small distillation. So we've got just the condenser really. We don't have the little this bit coming off the end because I thought we didn't really need it. It's just going to add a bit more space for like water droplets to get stuck and become unrecoverable. Anyway, it's just about boiling now, so we'll connect up the condenser water pump, and we should start getting some drips down into this beaker. First couple of drips coming over now. Yep, there we go. Nice. So while that's all going ahead nicely, there are two things that I wanted to do. The first one is show you the next 3 cells that I have ready for the next 3 stages of deuterium enrichment, because pretty soon after we do this and keep electrolyzing down in this cell over here, we're going to really run out of space in that cell, and we're going to need to start putting the heavy water into smaller cells. And so that's what I've set up over here. You can see once again I'm using 50/50 lead tin solder as my electrodes. I've stretched it out into like these nice long wires, which should work really well, have a nice high surface area. Anyway, our first cell is this one. You can see all it is just a small tube with the 2 electrodes inside, pretty similar to all of the other cells I've made. The next couple are the same, but they're just smaller each time, because once we reduce the volume down to say there, we're going to want to swap it into this cell, just to keep that the surface area on the cathode, the one that will be generating hydrogen, keep the surface area nice and high so that we've got a good separation between hydrogen and deuterium. I haven't siliconed all these up yet, just because I'm going to have to add the gas vent tube, but these should be ready to go by the time we finish with this cell over here. So that's all very good. Now the second thing I wanted to do is using sodium carbonate as an electrolyte isn't all that good, because at the end we always have to neutralize it with sulfuric acid or sodium bisulfate, which is really just adding hydrogen which isn't enriched in deuterium, which isn't a very good idea once we get past this stage here. So what I'm going to do is, for future electrolytes, I'm just going to use sodium sulfate directly. However, last time I did that, the electrodes didn't seem to hold up very well. So I'm thinking that maybe the sodium sulfate that I've got is a little bit impure. So what we're going to do is recrystallize this sodium sulfate that I have, and then see if we can dry it out on this hot plate. So I have set up some water to boil on my hot plate, and once that gets hot, we'll add our sodium sulfate, keep adding water till it all dissolves, and then we'll let it cool down, and then hopefully all of the sodium sulfate should crystallize out, and we'll be able to recover our pure sodium sulfate. And I've dissolved all of the sodium sulfate in pretty much just enough water to have it all dissolved. So in a second I'm going to filter that just to remove any solid impurities that are there right now. The distillation is going well. We've got about 40 milliliters of water that's distilled off at this stage, so I'll leave that going. That's going very nicely, and I'll just filter this off. So there is our very hot sodium sulfate solution. I'll let this cool down, and hopefully we'll get some sodium sulfate crystallizing out in a little bit. Now our distillation is done. I think we got around 140 milliliters of water all up, so that's pretty alright. There's a bit more than I expected. It means that we're going to have to do a bit more electrolysis with this jar than I thought we were, but also our sodium sulfate has all crystallized out in there. Looks very nice. So I'll filter those out of solution, and we'll try to dehydrate all of that, and we'll just have to discard the solution that they're a part of, because that's going to contain all of the stuff that's not sodium sulfate. And so after decanting the solution and washing the crystals a couple of times with some cold water, you can see those nice big sodium sulfate crystals. They always look very nice. Too bad we're going to have to, well, essentially destroy the crystals in order to make the dehydrated form. So I'm going to put this on the hot plate and just turn up the heat just a little bit, and we'll see if we can dry off these crystals. And in 20 minutes or so, those nice sodium sulfate crystals have been reduced to this kind of still slightly wet, but it's white powder. We can do this with sodium sulfate because it doesn't really decompose at these temperatures. Most other salts you'll actually have to evaporate down and then like put it in a desiccator or something in order to get it dry, but with sodium sulfate it's nice and easy. We can just heat it up, and we have here our, well, concentrated heavy water that we have. Well, this took a year to make, and we'll keep concentrating that down. As soon as we've dried out this, we'll put maybe like a teaspoon or so of sodium sulfate into the water, and then continue electrolyzing it with our electrolytic cell. And that is pretty much all of our sodium sulfate, as dry as we can get it. You'll notice we have lost quite a bit of it as you do with recrystallizations, but that's alright, that's not a difficult chemical to make. We put a teaspoon or so of that into our heavy water, and I'm just dissolving that up now. And now that that's all dissolved, I'll stick all that in there, maybe 70 mils or so in the inner chamber, and then electrolyze that down. Do the next 70 mils, electrolyze that down until we reach 50 mils total, and then we'll stick it in there, electrolyze it down to 5 mil, stick it in that one, electrolyze it down to 2 mil, and then stick it in that one and electrolyze it down to probably less than 1 milliliter. Should only take a month or two, and it's all ready to go. And it's now down in the cooler bath, bubbling away happily. I've got it running at about 1 amp, and I'll leave that for maybe the next 4 days, and I'll check on it and just keep on going. I'll come back in 4 days, check on it, but I think I should just be able to leave it going for the next week or so. Other than that, and then maybe by next weekend we might have electrolyzed down enough to start using this cell, but I don't know, probably not. So a few people in the comments over the last few episodes of this series have asked me to go over the maths as to the deuterium enrichment process. So I think now is a good time to go over all of that. The deuterium enrichment that we're doing with electrolysis is based around the Rayleigh fractionation equation, I think it's called. So I'll write that out. So this here is the Rayleigh equation. What it is an equation that gives you the concentration increase of your isotope after you perform a certain enrichment process. What it gives you is the increase in concentration, or A, based on the volume that you've got left over. So in terms of electrolysis, if you electrolyze a solution down to half its volume, then this B, or the volume that's left over, will be 0.5 or a half. And then C up here, that is the separation factor. That's the value that we don't really know, but from sources online we can tell that electrolysis of water gives us a separation factor between hydrogen and deuterium of between 5 and 10. So what that means is electrolysis is between 5 and 10 times more likely to pick out a hydrogen atom out of water rather than a deuterium atom. So now say you, like before, electrolyzed a solution of water down to half its volume, so B is equal to a half. We can work out the increase in concentration of deuterium based on what our separation factor is. Now, because we don't know what our separation factor is, probably between 5 and 10, we're going to have to do multiple calculations using different separation factors in order to get like a range of results. So maybe we'll start out with C equals 5, that's the worst case scenario. We'll go C equals 8, that's somewhere in the middle, and we'll have C equals 10, that's the best case scenario. Plugging all those into the equation, we get A equals a half to the power of 1 on 5 take 1, A equals a half to the power of 1 on 8 take 1, and A equals a half to the power of 1 on 10 take 1. Plugging those into the calculator, we get, at a separation factor of 5, 1.7411. Separation factor of 8 gives us 1.8340, and at a separation factor of 10 we get 1.8661. So what this tells us is that if we electrolyze a solution to half its volume, the resultant deuterium in water will be between 1.74 and 1.87 times the concentration that it was in the initial full sample of water. Now if you think way back to what we were doing a year ago, where we had like a jar full of 400 milliliters of water, and then we'd electrolyze that down to 200 milliliters, so increasing the deuterium concentration by somewhere between this number and this number. What we did then was we topped up the solution with regular water back up to the 400 milliliter line. Of course, in doing that, we did decrease the concentration of deuterium each time we did that. We did that 10 times for each set of electrolysis runs that we did. So from that little step that we did, adding the regular water, we find that the concentration of 400 milliliters after we've electrolyzed it down to 200 and then added 200 more milliliters of regular water, we find that the final concentration of one of those cycles is the initial concentration plus 1 over 2. It's pretty much just the average of your concentration of enriched 200 milliliters plus the concentration of your non-enriched 200 milliliters, and you get your average concentration C. So say we had 200 milliliters of 1.8661 times concentrated deuterium, and then added 200 milliliters of regular water with just a concentration of deuterium of just 1 times the normal concentration. We get an average of, if I write it all out, and so our final 400 milliliters of water will give us a concentration of deuterium that is 1.433 times the initial concentration in regular water. So now you might think that seeing as we did this cycle of electrolyzing down and then topping back up 10 times, we might just be able to do 1.433 to the power 10. However, it is quite a bit more complicated than that. What we actually have to end up doing is the concentration, all right, after n cycles, say, is a sequence where the concentration after n cycles is equal to the concentration of the previous cycle times our value for A plus 1 all over 2. Now this takes into account the electrolysis enrichment factor and then diluting by the 200 milliliters that we add. The only thing we have to say here is, because we're working in terms of the initial concentration, where the initial concentration we'll say is equal to 1, we just say the concentration after 0 cycles is equal to 1. Now this can be simplified to this. Now we can easily work this out on the calculator. If we just type in 1 equals, this will give us the initial concentration for the deuterium that we want. Now we can type out our equation here on the calculator. I think I'll use the A value for C equals 10, or a separation factor of 10, just to start off the calculations with, and then we'll work our way out from there. And so here we have our equation just typed out on the calculator, and if we now press the equals button 9 times, after 9 cycles of that electrolysis and then topping up, we had a sample of water, 400 milliliters, that was 4 times enriched in deuterium from the initial concentration. After those 9 cycles, back a year ago when we were actually doing this, we then just electrolyzed down those 400 milliliters down to 200 milliliters. So we can just multiply that number by 1.8661 again, and then in the final 200 milliliters after our 10 cycles of electrolysis, we had deuterium content of 7.467 times the initial concentration. And so now with a little bit more light, plugging this calculation into the calculator, plugging it in 10 times because we did 10 electrolysis cycles, we get in the final 200 milliliters at all these different separation factors, we get a concentration of deuterium that is at worst 5.294 times the initial concentration, and at best it's 7.467 times the initial concentration. So now, after obtaining the 200 milliliters of our concentrated deuterium, what I ended up doing way back when I was doing this stage is I did that 8 times, and so I got in the end 1.6 litres of this, somewhere between 5.3 and 7.5 times initial concentration of deuterium water. So I managed to get quite a bit of it. And after that was done, I stopped doing this process where I was electrolyzing down and then topping up, and we just straight out electrolyzed down the 1.6 litres of water there, which makes the calculation a whole lot simpler because we don't need to use this complicated sequence, and we can just use our original Rayleigh equation to figure out the concentration of deuterium in the final amount of water that we're going to get. Now, even at these relatively high concentrations of deuterium in our 1.6 litres of water, we still need to enrich the deuterium content to around over 6,000 times the initial concentration. And so based on what we have here at these different separation factors, we still need to, if the separation factor was 5, we still need to increase that concentration by a factor of 1,209. And for separation factor of 8, we've still got to increase it by 938 times, and a factor of 10, we need to increase it by 857 times. And so now, using our Rayleigh equation again, we know what A has to be. It has to be 1,209 for a separation factor of 5, it has to be 938 for a separation factor of 8, and 857 for a separation factor of 10. And so, subbing in those values for A and C, we can solve for B, which is the fraction of the volume that we have left over after electrolyzing our 1.6 litres. And so, using the Rayleigh equation up here, we've got our values for C, 5, 8 and 10. We have our values for A as 1,209, 938 and 857. We solve for B, and we find that the volume of water that we need to end up with as a fraction of our 1.6 litres. At the end, if our separation factor is 5, we need 0.0001403 times that volume. Similarly, for 8 and 10, we need 0.0004010 times our 1.6 litres, and 0.0005509 times our 1.6 litres, respectively, for the 8 and 10 separation factors. And so by multiplying our 1.6 litres by these fractions, all right, at the very end of our cycle, okay, worst case, separation factor equals 5, we will get 0.225 millilitres of pure heavy water. It's not going to be perfectly pure because you're never going to get rid of all of the regular hydrogen isotopes, but it will be effectively pretty much 100% heavy water. That is the worst case, and it's not all that good. That's only like, 8 drops, but it will be pretty cool. It will be doable to get like 1/4 milliliter out of our electrolysis cells, so that's good. Best case scenario, where separation factor equals 10, we've got 0.88 milliliters, or maybe 1 milliliter at 90% heavy water, which would be pretty good to have. At a separation factor of 8, middle of the two, we get a bit over 0.5 milliliter. So either way, we'll get enough heavy water to see and do a couple of tests with. So now the thing that actually determines the separation factor is pretty much your current density and your electrode material. Now, at the very start of the electrolysis, when I was doing the 10 cycles and then getting the 200 milliliters of enriched deuterium water, I probably did have a pretty low separation factor. We'll say it's 5, we'll say it's the worst case scenario, because I was using, I'm not sure what the metal was in the electrodes that they were, because those were, I bought them as platinum electrodes and they turned out not to be platinum, so I ended up using them just for the heavy water generator. I'm not sure what they were, so we'll just say that the separation factor was 5 at that stage, because I was also running them at a really high current. So we can say that we probably did only have 5.3 times the initial concentration in the 1.6 litres that we had after the first stage of enrichment. However, after that, I have been electrolyzing it down really slowly with lead electrodes, and lead I've found online, I'm pretty sure they have a separation factor around 8. So up to this point, we probably had a separation factor of 5, but from this point onwards, I'm pretty sure we had a separation factor of 8 or above. And so redoing the calculations, instead of our factor being 938 for the separation factor of 8, we will change that to 1209, and we'll just find B is equal to 1209 to the power of negative 8 on 7, which gives us apparently 0.0003, pretty much exactly. Multiplying that out by the 1.6 litres, we get 0.48 millilitres, or around half a milliliter of pure heavy water. So this half a milliliter of heavy water is what I'm going to expect to get out, because that's like worst case scenario, and then we're going off what the literature says online as to the separation factor of hydrogen and deuterium on a lead electrode, and hopefully maybe we'll get more than half a milliliter, but we'll electrolyze until we reach half a milliliter of water, and it should be pretty much pure. Well, there you go. I hope it wasn't too confusing, but after a year's worth of work, we should get half a milliliter or above heavy water. See you later.